Okay, just wanted to again remind you, we're talking about this entropy stuff. You can't visualize it. If you see the numbers, they don't make any sense to you. Okay, I understand that. But here's the principle. Here's what I want you to remember, and I'm going to keep pounding this over and over and over. And hopefully, at some point, you're going to go, oh, okay, I get it. This is why we're studying this entropy stuff. I'm not trying to do it to make it more confusing. I'm not trying to do it to just add more busy work. What we're trying to do is understand this principle. Efficient processes generate less entropy. Since entropy is a property and can be measured, we have a measure of efficiency. Okay, and that's really the key principle. Okay, entropy is a property, we can measure it, therefore we have a measure of efficiency. Okay, now, as we've been looking at, the only thing I know right now going into this is I can get entropy from the tables. Okay, if I know refrigerant 134A, I can get entropy that way. If I know water, steam, right, I can get entropy that way. That's all I know right now. Obviously, we need more than just that, though, because what if we have liquid water? What if we have a solid? What if we have gases? How do we get entropy? Okay, we need some other ways. Okay, so since this is such a kind of an important equation, and I think kind of an interesting one, I wanted to kind of show some background here and show how we derive some of the key formulas for getting the change in entropy for liquids, solids, and gases. Okay, and so it all starts off basically with something that we should be familiar with. Okay. That right there is the first law for closed systems. Notice it's for closed systems. By the way, we lose nothing by assuming this, but basically it's the first law of thermodynamics. Q minus W equals change in U. All right. So we're writing it in differential form. dq minus dw is equal to du. Okay? That's just the first law. That should be easy. Now, take a look at these next two equations. We're going to make two substitutions. I'm going to highlight them in green here. The first one should be obvious. Remember what I said? What's the definition of entropy? I said entropy ds is equal to dq over t, right? Well, then you can also write dq equals tds, which is what I have highlighted in green there, right? The other one is, remember I said that you need to memorize this one? I don't ask you to memorize much in this class, but I do ask you to memorize that. The work, thermodynamic work is equal to integral PdV, right? I promise I don't ask you to memorize more than like 5 things in this class, and that's one of them, okay? And then we can write that as a differential. Differential work is equal to PdV, right? So what you can then do is you can take those two things and substitute it into the blue equation. Very simple here. There's not complicated algebra or any tricks or anything like that. And you can get the form below it. It basically says differential ds of differential entropy is equal to du over t plus pdv over t. Okay, whatever. That's just some equation. But it's actually really helpful because we're going to use that equation to derive some very important formulas for us. Okay? For liquids and solids, we can simplify this equation. We can write dV is approximately equal to 0. And I have a question. Why? Any ideas? For liquids and solids, change in volume, differential change in volume, is approximately equal to 0. What's that? Because the book says so? What? No, I'm sorry, I didn't hear what you said. What was it? What?
Because molecular structure is a lot more stable than gas.
Nah, not really. I mean, there's definitely lower entropy. Yes. What's that? The volume doesn't change much. Yeah. Why? Well, because we generally assume liquids and solids to be incompressible. Okay. If you take water, let's say you got a bucket of water, okay, and you put that thing under tremendous pressure. Does it change volume? Not really. Okay. If you take a bunch of air and you put it under tremendous pressure, does it change volume? Yes. If you put air under a lot of pressure, you can really compact it. Okay. you can really compact air. Okay, you can change its volume very easily. You can compress it into a very small volume. You can't do that with liquid water. Okay, that's why we have hydraulics. Okay, I mean, think about the kind of pressures that hydraulic things have. Okay, it's just water inside, basically. Okay, maybe not exactly water, but whatever. Okay, and so it's a liquid. Okay, it's a liquid, and you put it under tremendous pressure, and it doesn't change volume. Okay, that's the power of hydraulics. Okay, it doesn't change volumes. Okay, now you have pneumatics too, but you can't put pneumatics under those same kind of pressures. You can't get the same thing out of pneumatics. Okay, because no matter how much pressure you put on a liquid, it really doesn't change volume. Okay, try it sometime. You know, I did that when I was in fluids class. I had one of these things. I mean, it was a silly little thing, but I had a 2-liter. You ever seen one of those 2-liters that has the you can put a little thing on the cap of a 2-liter and it has a little pump on it. And the idea behind it was, because I hate buying 2-liters. I don't know about you, but I hate 2-liters because every time I buy a 2-liter, I drink a little bit of it and then it goes flat. Okay, so they had one of these things that you could buy and screw on the top, and you could pump up the 2-liter, and you could pump up the pressure inside that 2-liter. And I think the idea was, and I think it sort of worked, is that if you have the contents under high pressure in the inside, then the pop, you know, whatever carbonated beverage it's inside, will not lose its carbonation so much because there's a lot of pressure above it. And so that's true. I mean, if you pressurize that thing, the carbonation, the oxygen, you know, the carbon dioxide won't want to come out of it so much, right? It will stay inside. Okay. So what I did one time is I thought, okay, what I'm going to do is I'm going to put this thing under as much pressure as I can and see if I can compress the water. And you really can't. You really can't compress the water. It doesn't change. No matter how much pressure you put on that thing, you really can't change the volume of that water. Okay, it's just going to be what it is. And then, so that's true. Since that's true, you can take out dV in that top equation there. Okay. The other thing is this: du equals c dt. Well, that's just specific heat, right? That's just specific heat. That's very simple. I don't usually write it that way. Normally, I would write this: change in U is equal to C times change in T, right? But then you can also write that as a differential. du equals C dt, right? Same thing, right? Okay. So you substitute both those relationships in here, and then you integrate, and you get this following form. And this is a form that I'll give you on your equation sheet, so no need to memorize this, okay? But that form is for the entropy change of liquids and solids, okay? Now, notice that specific entropy, little s, right? So this is per mass. This is per mass, okay? So the units here are going to be kilojoules per kilogram K, because it's going to be per mass. Okay. Okay. So that's a very important equation. Anytime you have a liquid or a solid and you need an entropy change, boom, there's your equation. There's your analysis. Next, gases. We deal with that a lot too. Air is our most popular one, but we have other ones as well. For gases, without loss of generality, we could make the following substitutions. Remember, with gases, you have two different types of specific heats. You have C sub V and C sub P. The C sub V has to do with du, right? That if I want the change in internal energy, the change in U, I have to use C sub V. If I want the change in H, I have to use C sub P. And by the way, if you forget that, that'll be on your equation sheet. Don't worry. But you know, that's probably should be something you know. Also, of course, anytime we have gases, I can't escape ideal gas law. I've got to feel like I got to use it, right? If you substitute both those relationships into that ds equation that I have up top, right, you can derive the following form for the change in entropy of a gas. Okay? And you might see that C sub V in there and go, hold on a second. That C sub V, wasn't that only when I had a closed system that I used C sub V? Yes, that's true. If I need the change in internal energy, I use C sub V for a closed system. But this can be applied even for control volumes, anything. It just comes from basically, regular energy analysis. So there's nothing that you lose here. There's no loss of generality here. Okay? But by the way, we can make another substitution here. We can also substitute the fact that H equals U plus PV, okay, in there, all right? And we can use that fact as well, and we can use the fact that change in H is equal to C sub P times delta T. We can take both of these and derive the other equation there too. And again, everything I've got boxed in red will be provided for you on an equation sheet, okay? So we can basically derive that form as well. Now, both of these equations can be used whenever, okay, to get the change in entropy of a gas. Why would you use one versus the other one? Problem. Notice that both of them have temperatures, but the top one of these two has specific volumes, whereas the bottom one of the two has pressures. So if you knew the pressures, you could use the bottom one. If you knew the specific volumes, you could use the top one. Okay, so that's the only reason. It just depends on the information given in the problem. Okay. With all of these equations, and again, the ones I've got boxed in red, you will be provided, no need to memorize any of those. With all of these, we're going to assume constant specific heats. Is that always true? Not really. By the way, if you go in the book, they give you other ways to do it. If you don't assume constant specific heat, there are other ways to do it.
There were long-winded formula.
There's longer formulas, yes, there are. I figure I'm throwing so many formulas at you that let's just go with this. This is close enough. In fact, the book has an example that shows you the difference between the constant specific heat assumption, this, and a non-constant specific heat function assumption, and there's only slightly different. Of course, if it's a large temperature range, it may be a bigger difference. But, honestly, by the time this class is over, your equation sheet is 2 pages long. So do I need to give you more and more? I try to cut down on some of the things as much as I can, because there's already 2 pages of equations by the time we get done with this. And students are like, oh my gosh, there's so many things I have to sort out in my mind and figure out whether I use this or how I do this. And I figure it's probably best not to get anything more complicated, okay? But these are going to give us the entropy changes when we need them for liquids, solids, and gases, okay? Let's go through an example. All right, so we've got here some kind of bar of iron. It's 50 kilograms, fairly large, yes. And it's at 800 degrees Celsius. Okay. And we've got a tank of water. It is 5,000 kilograms. And initially at 25 degrees Celsius. Okay. And it says to determine the amount of entropy produced. Okay. That's also called entropy generated. Okay. And recall the following analysis. If I want the amount of entropy generated, Sgen, I'm going to need the change in entropy of both things that are involved. In these problems, there's almost always 2 pieces involved. There could be more than 2 pieces, but generally there's 2 pieces. In this case, it's the iron and the water. So it's going to be the change in S of the iron plus the change in S of the water, right? That's going to get the total entropy generated. Since the iron gets colder, right, the iron's going to cool off when it's quenched in the water, right? I'm going to assume, obviously, the iron temperature goes down. That's the whole point of quenching, right? that means that the entropy of iron will go down because the temperature of iron goes down. Okay? The water temperature will go up, right, because it will receive heat from the iron, right? And so the entropy of the water will go up, okay? But the total net will have to be 0, but it won't really be 0. It has to be positive, right? Because this is not a reversible process. If I take iron at 800 degrees Celsius, put it in water, and I pull it back out again, it's not going back to 800, right? That's not going to happen, right? It's not reversible. Once you quench that iron, it's not coming back to 800 degrees Celsius unless you put it back in the furnace, right? So this is not a reversible process. So S-gen has to be positive, okay? Has to be positive. Now, I think the most important part of this problem is actually the first part of this problem. There's two parts of this problem, all right? The first part of this problem is something you have to know in order to pass this class. The second part of this problem is something I would like you to know, and certainly you need to know how to do in order to get an A, okay? But you've got to be able to do the first part of the problem, okay? If I tell you, if you go back to these formulas, look, it says I need to get the change in entropy of iron and the change in entropy of water, right? Let's take a look at the formula for liquids and solids. Right here, all right? It's the top one I boxed in red. What are the two things I need to know to get S2 minus S1? Well, three things, but I obviously need to know the specific heat. What are the two things I need to know besides specific heat? The temperatures, okay. Now I'm given, obviously, the initial temperature, T1. How am I, and this is a very important question, if you can't answer this now, I sure hope you can answer this when we have the test. And even if you can't answer it when we have the test in a few weeks, you better be able to answer this on the final, okay, or you probably won't pass. How can I get the final temperature of the water and the final temperature of the iron? And I'm going to give you a clue. I'm going to assume they go to the same final temperature. Is that really true? No, probably not. The iron probably doesn't get all the way down to the temperature of the water. But if you did it long enough, right? If you dunk that iron long enough, it may take an hour or two, eventually they're going to get to the same temperature. Let's just assume that happens. So how, if they get to the same temperature, how am I going to get that temperature? That's what you need to be able to answer. Specific heats have to be a part of it. That's good. What are we doing now? What are we going to do? Like, okay, I just tell you right now, give me the final temperature of this. Okay, and there's lots of different ways to say the first law. Energy in equals energy out, whatever, okay? In this case, you could say energy in equals energy out, but it's really probably a better way to say it is the change in energy of the iron is what causes the change in energy of the water, right? The energy goes from the iron to the water. Everybody see that, right? Because the iron heats up the water. Okay. How can I write the change in energy of the iron? We would call it internal energy, but even if you didn't know that, if you just said, oh, it's this energy, the iron cools off, how would I write that? Yeah, C delta T, right? Yeah, I mean, it is equal to energy gain, but you're right. It's C times the delta T. So it'd be T2 minus T1. So this is going to be, let's just say it's iron right here, and this is the C specific heat of iron times T2 minus T1. Okay, now let's fill in some blanks here. Okay, so the change in energy of the iron is equal to the specific heat of iron. Yeah, you got to look that up. You do have tabular data for specific heat of iron. You got to find it back. It's in kind of in the front, I think, of the charts. Okay, table A3. Iron, specific heat, 0.45. Okay. Kilojoules per kilogram K times the change in temperature of the iron. Yeah. Notice, where's the mass in this, too? We'll get to the mass in a second. what's T2? T2 would be the final temperature, right? I don't know what that is, so I'm going to just leave it as T2. What's the initial temperature? 800. Yeah, and it is okay to leave it in Celsius. Okay? Now, question here. What about the mass? Yes, I have to put the mass in here. I'm given the mass. And notice the units on specific heat. It's per kilogram. But I know I have 50 kilograms, so I might as well go ahead and multiply that. Okay? So I got 50 kilograms. Okay? Really, this is C times change in T times M. Okay? So I don't know that numbers yet, but let's do the other one. Let's also do change in energy of the water. Not exactly. Why aren't they exactly equal to each other? That's a great. They are equal to each other with one little caveat. Why are they not exactly equal to each other?
Because you can't have a zero entropy change.
No, we're not talking about entropies at all.
Oh, there were some of the oils.
No, you're saying the change in energies are equal to each other. And I'm saying, yeah, but be careful, because one's going up and one's going down. So,
Oh, plus each other.
yeah, right? Because they are the same number, but remember, one's negative, one's positive, okay? So be careful when you set them equal to each other. You can't exactly set them equal to each other, okay? Because one's negative, one's positive. Okay, so change in entropy of the water is going to be, I'll keep consistent, specific heat of water, right, is 4.18 kilojoules per kilogram K. The final temperature of the water is T2. The initial temperature of the water is 25 degrees Celsius, right? And the mass of the water, is a lot of water, 5,000 kilograms. Okay? So now, what you're really saying here, remember the water is going to be a positive, the iron is going to be a negative. So what you're really saying is change in U iron plus change in U water equals 0. So what that's really saying is, I'm going to drop the units just to make the math a little quicker. 45 times 50 for the mass, T2 minus 800 plus 4.18 times 5,000 for the mass times T2 minus 25 equals 0. So now I put it together in one equation, and now I want to solve for T2. And you can, it's not that hard, it's just some algebra, right? If you were to go through this, you could also use your solver, which is kind of what I did. I thought that was kind of fun. I used my solver, and I got this for T2. I got temperature 2, the final temperature that they go to, as 25.83 degrees Celsius. 25.83. Make sure that's a clear spot. So the water doesn't get heated up that much, right? I mean, the water was initially 25 degrees Celsius, and it only gained not even a degree of Celsius. But remember, the water was huge, right? And the iron bar was fairly small. So, yeah, and specific heat's almost 10 times what iron is. So, you know, that kind of makes sense. There's so much more water. Well, you can do it algebraically. You just have to write it all out and solve for T2. I mean, it's just algebra. You could do it. If you have trouble, come see me in my office. I'll help you. It's not too hard. Okay. So the water heats up a little bit. That may seem trivial, but let's say you're an engineer at a materials metal processing plant, and you're doing one of these quenches, every few minutes. Well, if you keep doing this, you're going to keep heating that water, right? Every time you're going to heat that water. And so as you keep doing it, all of a sudden that water may get hotter and hotter and hotter if you keep doing this. And so, it may seem trivial to do it once, but if you do it hundreds of times a day, you're definitely going to heat up that water fairly significantly, okay? And you may start to boil it off and things like that as well. So you probably, if you design this thing, would have to have some kind of system to replace some of the water to keep it at a better temperature, okay? But quenching, as you learn in materials, is an important process to harden steel, or iron, whatever, iron, steel, whatever. Okay, so that's the final temperature. Now, the rest of this is pretty trivial. Okay, now again, note these formulas here. This formula S2 minus S1 for the change in entropy, I have the temperatures now. It's C times ln T2 over T1. But remember, that's per mass, so I have to multiply by mass. Okay? So let's do the rest. This is pretty simple. Okay? Let's get the change in S of the iron. Okay? All right, that's going to be the C of iron times the mass of iron times the natural log of T2 over T1. Okay? That's going to be 0.45 kilojoules per kilogram K times the mass of iron, 50 kilograms, right? Times the natural log of the two temperatures. Now, whenever you divide by a temperature or multiply by a temperature, what do you got to do? You have to put them in absolute, right? You have to put them in absolute. You cannot put Celsius in here. Whenever you divide or multiply by any temperatures, they're always going to be absolute. Because it doesn't make sense to divide by 0 degrees Celsius. That would be undefined, right? So it has to be in Kelvin. So we're going to have to take both those temperatures. The initial, well, let's do the final temperature. The final temperature there is 25.83 degrees. If you do 25.83 plus 273.15, that converts it to Kelvin, right? You get an actual T2 of 298.98. Try to make that nice. Okay? So that's the same thing there converted to Kelvin, okay? The initial temperature, by the way, is 800 degrees Celsius. If you convert that to Kelvin, you get 1073.15. Okay? If you plug and chug that one, now we're just plugging and chugging, right? There's nothing to it. You get minus 28.75 kilojoules per Kelvin. Okay. Is that good? Is that bad? I don't know. Okay. That's the hard part about entropy. When you calculate it, you kind of go, okay, whatever, right? I mean, what meaning is that? At least when you calculate things like temperatures and pressures, you probably can put meaning into it. If you calculate a pressure and it's 3 megapascals, you go, oh, well, that's like 30 times regular pressure. Okay. So it's stuff like that. But with this, you have no, what does that mean? I don't know. So, but obviously the iron goes down in entropy. So the water must go up. So let's do that. Change in S of the water. It's going to be the C of the water plus the mass times the mass of the water times the natural log T2 over T1 of the water. The changes of just the water. So specific heat of water, 4.18 kilojoules per kilogram K. The mass of the water is big. It's 5,000 kilograms. And so then this is multiplied by the natural log of the two water temperatures, which are pretty much the same. I mean, they're very close. Obviously, they're not exactly the same. But the final temperature of the water is the same as the final temperature of the iron. That's the 298.98. The initial temperature of the water is 25 degrees Celsius, right? Plus 273.15. So that's going to be 298.15. So they're almost the same. If they were the same, the natural log of 1 is 0, and there wouldn't be any entropy produced. But obviously, it's a little bit different. And so when you multiply that by 5,000 and multiply by 4.18, it will still be a fairly significant number. It turns out if you do the math, you get this as 58.10 kilojoules per K. Now it asks for the S-gen. The S-gen is actually pretty simple. You just have to add the two. The change in S of the iron, right, plus the change in S of the water. And you get 29.35. And again, the only meaning you can grab out of that number is if I had another process that had less entropy, I would say that that other process was more efficient. But there's no meaning in that number by itself. It's not like I can look at that number and go, oh, that's good, or that's bad. I have no idea, right? So don't worry about it. If you look at this and go, I don't know what I'm doing, I'm just calculating numbers, that's okay at this point. We're still kind of going through that phase. This, or I could see the point of this because I can see here why this would be helpful. Okay? But in this level, you're just cranking out numbers and you kind of go, oh, okay, that's just kind of what it is. Okay. Questions? No?